Just 1 second.
Okay.
Okay.
All right. So our second speaker is Liujun Zou from Perimeter Institute, and he's going to tell us about Hamiltonian tomography via quantum quench. Liujun, go ahead.
Thanks. Thanks for giving me the opportunity to present this work. The talk will be based on this paper done with these two amazing collaborators, Zhi and Tim. So let me first try to motivate you by asking you this question. Do you think if it's possible to dive in the future? For example, if I go to a wizard and the wizard asks me what was happening 10 minutes ago, and I say I was listening to last talk 10 minutes ago. And then the wizard asks me what's going on now. I will tell him I'm giving the talk. Then the question is, do you think if it's possible that wizard can know everything about me, including the past and even the future? I will not address this question, but something I will discuss later has a similar flavor. Another source of motivation comes from quantum simulation. Say we have such a many-body Hamiltonian that is of interest to condensed matter physicists. However, maybe in solid-state systems, it's not easy to realize such a Hamiltonian. And after it's realized, it may not be easy to control the Hamiltonian, to control the parameters of the Hamiltonian. Then the AMO community, starting from this paper, proposed that one can actually use cold atoms in optical lattices to simulate such Hamiltonians. And the great advantage of doing that is the high controllability. Here I'm taking a picture from this theoretical paper. You can see there are some atoms with different hyperfine states, and they are living in some optical potential created by some lasers. That was the proposal. And after a couple of years, the proposal was experimentally realized, and this is a beautiful picture from the experimental paper. So all these pictures are very, very beautiful, but the real experimental platform may be like the one here. It's very complex. So you may wonder, when you are doing something so complex, you may wonder, how are you sure what you are simulating in the lab is really what you want to simulate? Although when you have some proposal to simulate some many-body Hamiltonian, you have some idea of the form and the parameters of the effective Hamiltonian, but it's still nice if you can have a direct way to measure the many-body Hamiltonians. Okay, so I will tell you two results. The first one is more of conceptual interest. I will argue that we are able to determine a many-body Hamiltonian from a single initial and final states related by the Hamiltonian evolution. But this one is more of conceptual interest. It's not really practically very useful. So in the second part, I will tell you a more practical way for Hamiltonian tomography. Okay, so let's start from the first one. This is kind of similar to the first question I asked you. The question is the following. In the first or second class of quantum mechanics, we learned that if we have an initial state and we know the Hamiltonian, then by applying this formula, we can obtain the final state. Now I want to ask the inverse question. Suppose I only give you a single pair of initial and final states related by the evolution generated by this Hamiltonian. And the question is, can this Hamiltonian be uniquely determined? This question is also partly inspired by some related work that uses a single eigenstate to determine or single steady state to determine the Hamiltonian. And the main difference between these two approaches is that an eigenstate is a special state that doesn't change under the Hamiltonian evolution. But here, what we are using is precisely how the state changes on the Hamiltonian to gain some information of the Hamiltonian. In particular, the initial state we will choose can be generic, and it doesn't even have to be pure. It can be a mixed state. So if I ask this question, maybe your first thought would be, this is of course not possible. It's quite counterintuitive because how can you know the entire history of some time evolution just based on the states at 2 moments? This intuition is correct, and a more formal way of saying it is the following. Suppose we consider a system with V qubits, and then the number of parameters of the Hamiltonian will be of the order 2 to the 2V, and the number of parameters of a state will just be 2 to the V. Then when V is very large, which is true for a many-body system, 2 to the V is much smaller than 2 to the 2V. This is telling us to determine the Hamiltonian from the state, the problem is underdetermined. So in general, you should not expect to be able to determine this Hamiltonian. However, after some thought, you may realize after all, we are not interested in determining a generic Hamiltonian anyway. We are more interested in a physical Hamiltonian, which often is local. That is, this Hamiltonian can be written in terms of a summation of some local operators. Let me mention in this talk, we are kind of using unconventional terminology. By locality, we do not necessarily mean spatial locality. We really mean few bodiness in the interaction of the Hamiltonian. For example, the SYK model that involves 4 interacting Marianas in each term is also called local in our sense because it's a 4-body Hamiltonian, although every spins can interact. Okay, so for such a local Hamiltonian, the number of parameters in the Hamiltonian will scale polynomially as the number of degrees of freedom. Then when we have a many-body system, this number is much smaller than the number of parameters of a state. That is to say, to determine a local Hamiltonian from a state, the problem is overdetermined. So it gives us some confidence that it may be possible to really determine this Hamiltonian just from a single pair of initial and final states. Now the question is, how do we really do it? And we will just use a very straightforward method to do it. We will just use this simple observation that is under this Hamiltonian evolution, the expectation value of the Hamiltonian does not change. Furthermore, the expectation value of the Hamiltonian raised to any power does not change. So we have this condition here, I and F are initial and final states. Then we just plug in this decomposition of the Hamiltonian. We will obtain a set of equations for the coefficients C. So in this equation here, the repeated indices are summed over, and the C is some difference between the expectation values of some operators. More concretely, suppose we take small m to be 1, we get some linear equation of C. If we take small m to be 2, we get some quadratic equation of C, and so on. Then now we have such a set of equations, we can try to solve for C. And after solving for C, we will obtain the Hamiltonian. And notice we will not care about the overall magnitude of the Hamiltonian, but only the relative strength of each term. Because the initial and the final states are related by a Hamiltonian, this set of solution necessarily has this set of equations necessarily has a solution that corresponds to our actual Hamiltonian. Now we want to know whether the solution is unique. That is, we have a unique reconstruction.
Can you go back to the previous slide?
Yeah.
So how do you get these constraints, or what is it physically?
You mean here?
No, down there. This, yeah.
Here?
Yes.
I plug this equation into this.
Oh, m is the exponent. Is the so mth power of the like mth moment of the Hamiltonian is preserved.
Yeah, thanks. Let me clarify. So for each power m, I have a separate equation with a coefficient that has a superscript labeled by m. Does it answer your question?
Yes, thank you.
Okay. So then let's talk about the uniqueness of the solutions. And I will argue that for generic local many-body Hamiltonian, our method will give a unique reconstruction. And the argument goes with 2 steps. The first step is a mathematical result You can find the detailed proofs in our paper. Here, I just explain some intuition. The first step is the mathematical result that says, suppose we have giving a quantum system with a particular Hilbert space and a particular set of local operators, then we can show if one example of Hamiltonian that can be made of such local operators can be uniquely reconstructed, then almost all such Hamiltonians can be uniquely reconstructed. The intuition behind this statement is the following. Because now we have a problem of determining the existence and the uniqueness of the solution of some equation, and the equation is a polynomial equation. It turns out such existence and the uniqueness condition can be expressed as a polynomial of the coefficients of the equations we have. This may not be surprising because we note to determine whether a set of linear equations have any solution, what we have to look at is the determinant of the coefficient matrix. And the determinant of the coefficient matrix is a polynomial of the coefficients of the equation. So more generally, it's still true that for the set of equations we have, the uniqueness and existence of solutions are also determined by some polynomial conditions of the coefficients. And then you can use some analytical properties of the polynomial functions to show this statement. This is the first step. The second step is that now we need to find this particular one example of Hamiltonian that can be uniquely reconstructed. In this step, we will not be as mathematically rigorous as before. We will just be satisfied with some particular examples, maybe with finite system size. This is one example we checked. We also checked some other examples. So in this example, the Hamiltonian can be written as some poly X operator plus products of nearest neighbor poly Z operators. We can check, there's a mathematically mature method called globular basis under which we can check the uniqueness of the solution. It turns out it is unique. What this means is a generic Hamiltonian made of poly X and product of poly Z operators can be uniquely reconstructed. And it also gives us more confidence that more generically, a local Hamiltonian, local many-body Hamiltonian can be uniquely reconstructed using this method. You may already see this method has some important limitations. For example, technically, it's very difficult and sensitive. In particular, previously, we need to solve an equation, and the coefficients of the equation comes from the results of measurement of some expectation values of some non-local operators, which are experimentally hard to determine. So this is hard to measure. Even if you can measure them, you may make some errors in the measurement. Then we have to solve a nonlinear equation. This is already hard, and when you have some error in the coefficients, the solution may be off by quite a bit, and it's even possible you just lose the solution. So technically, this method has these limitations, although conceptually it's interesting. Also, it also has some, you can say, more basic limitation, and that is it fails in some fine-tuned case. For example, if the initial state is a steady state, then this method doesn't tell us anything because we are really relying on the change of the state under the Hamiltonian to determine the Hamiltonian. If the initial state is steady, then there's no change. And second is, often we are interested in a physical system which has some conserved quantity. If our system has a conserved quantity that can be decomposed into the same set of local operators, then we will not be able to determine the Hamiltonian uniquely, because you may recall the only thing that we used to determine the Hamiltonian is just the conservation of the Hamiltonian. If we have some other conserved quantity, generically our method will just give you some linear combination of the actual Hamiltonian and the other conserved quantity, which we are not able to disentangle. But let me also mention, translation symmetry does not belong to this case. On a lattice, the translation symmetry does give us a crystal momentum that is conserved, but it doesn't decompose into the local operator. So because of these difficulties, we would like like to have a more feasible way to measure many-body Hamiltonians. This brings me to the second part. Recall.
So you mentioned that you have successfully reconstructed the Ising Hamiltonian which have Z2 global symmetry. But later you mentioned that when there is a global symmetry, this construction is not good.
I mentioned if there's a conserved quantity, the construction is not good.
Okay, that does not mean the global symmetry.
It means continuous global symmetry.
Okay, thanks.
So recall the two technical difficulties. One comes from that we have to do non-local measurements, and the other comes from we have to solve nonlinear equations. We can get around these difficulties by, instead of using one initial state, we use an ensemble of initial states. For example, we have state percent 1, percent 2, until percent p. Now we evolve these states and obtain the final states. Then we use the condition that the expectation value of the Hamiltonian doesn't change to obtain a set of equations. So just again, we plug in this decomposition into this condition, we obtain such conditions. Notice here, this M is just some expectation value of local operators, not of non-local operators. And furthermore, here we are just having a set of linear equations. So the thing we have gained by using more states is that now we only have to do local measurements and we only have to solve linear equations. In fact, we don't even need to solve the linear equations because this equation also means the vector D defined here has zero norm. And you notice this MTM is a positive semi-definite matrix. Then after some thought, you realize this just means C is the eigenvalue of MTM with zero eigenvalue. That's also the smallest eigenvalue. So here I will normalize C to be to have unit norm. This method has a couple of advantages. First of all, it only requires local measurements, and the number of measurements that it requires turns out to be n squared, where n is the number of terms in the Hamiltonian. And if you have translation symmetry, it only has the number of measurements it requires doesn't scale with the system size. Furthermore, you notice in the last step, the problem of solving an equation is converted into a problem of minimizing the eigenvalue of a matrix. Solving an equation is not that good in the sense if you make some errors in the measurement, maybe the equations just have no solution. But if now you have a minimization problem, you will necessarily have some approximate solution. Furthermore, later I will elaborate that this method is stable against the errors from either preparing the initial states from the measurements and from some bad ansatz, and finally the fidelity of the method can approach 1 if we use more and more pairs of states. And let's look at this more closely. Let's first look at the stability of this method against the measurement errors. Suppose the actual Hamiltonian is here, and we use our method to obtain the coefficients of the equation M. But because this M is just some results of some measurements, we may have some error in these measurements. So M suffers from some error with typical magnitude epsilon. Then because of the errors, we obtain the reconstructed Hamiltonian we obtain is not the same as the actual Hamiltonian. And there may be some reconstruction error, which we identify as the sign of the angle between the C vector and the X vector. In our paper, you can find a proof that the reconstruction error is upper bounded by this quantity. Here, epsilon is the error, n is the number of terms in the Hamiltonian, p is the number of pairs of states, and lambda is such that lambda squared is the difference between the two lowest eigenvalues of this matrix. So lambda squared is the gap of this matrix. And it turns out when I define when I define it in this way, lambda doesn't scale with p when p goes to infinity. And the intuition behind this upper bound is also simple. Recall this C is the eigenvalue of the matrix MTM with the smallest eigenvalue. So C can be viewed as, if we view MTM as a Hamiltonian, C can be viewed as the ground state. Now MTM is changed, it's perturbed by some error. X is the new ground state of the new Hamiltonian. So we're just asking how much the new ground state differs from the original ground state. And you can analyze this just by the usual perturbation theory, and you can see such a bound. In particular, here you see the Fermionian energy denominator from the perturbation theory. This lambda is basically the energy denominator. So the lesson we have learned from this exercise is that to reduce the reconstruction error, we need to increase the number of pairs of states or this lambda. To increase the number of pairs of states, we just increase it. Let's ask, how do we increase lambda? Lambda turns out is determined by two factors. One factor is the evolution time. The other is the ensemble of the initial states. Recall lambda is the gap of the matrix MTM over P. And M is the difference between the expectation values of some operator. So when the evolution time is very small, the matrix M is also very small. So lambda is very small. So we want the evolution time to be larger to obtain a larger lambda. But making the time too large is also not very useful, because after thermalization for generic Hamiltonian, the local operators, the information of the local operators just doesn't change too much. So we do not gain too much after waiting for longer than the thermalization time. As for the initial state ensemble, we want to take advantage of more and more states. So we want the states to be very distinct from each other, but also it turns out it's not too helpful to make the states too random. For example, if you just take a random state in the many body Hilbert space, it turns out lambda would be very small in that case. And a good choice of the initial state is random product state written here. So I here labels a site, and phi I is a state on site I. For this choice, you can show lambda will be a constant when in such a limit. In particular, lambda is system size independent. We can benchmark this using here this generic two-body Hamiltonian. So this is a generic two-body Hamiltonian where the coefficients are taken from some random distribution between -1 and 1. Here we will also contrast our method with another method, which is proposed to do something else, but that method can in principle be used here. So in our method, we have p pairs of states, and we take a snapshot for each pair at time evolution time t equal to 1. In the other method, they only use one pair of states, but they take p snapshots separated by some time. We can compare these two methods in performing Hamiltonian tomography. And you can see from the figure here, for the same error, for the same measurement error, our method always performs better than the other method. And furthermore, in the limit where we use a lot of pairs of states, the reconstruction error scales as 1 over square root of p, as we analytically understood. So the intuition behind the disadvantage of the other method is the following. In the other method, they only have one pair of states, but they take many snapshots. So they want to make use of the many snapshots. Now the question is, what kind of time separation do they want to choose? If they choose the time separation to be too small, then there's basically no evolution between two snapshots. So they cannot get too much information of the Hamiltonian. However, if they choose the time separation to be too large, then due to thermalization, the local information will not change much. So if the time separation is too large, many of the measurements, many of the snapshots they take will also not be useful, as long as the snapshots are taken after thermalization. And that's a fundamental disadvantage of that method. We can also look at the reconstruction fidelity versus time. This fidelity is defined to be the cosine of the angle between C and X. Using the previous model, with this result, you can see for reasonable system size and within some reasonable evolution time, the fidelity approaches 1. And this saturation value of fidelity does not depend on the system size very sensitively. This is consistent with our previous explanation that for random product state, the factor lambda, the gap lambda, doesn't depend on the system size. Also, we can look at the dependence of the saturation time on the magnitude of the error and the system size. It also performs reasonably well. And we can look at another type of stability against bad ansatz. Recall, we have to start with a guessed set of local operators, but actually the Hamiltonian may contain some other operators. For example, OR may only contain 1 body and 2 body interactions, but O prime contains like 10 body, 11 body interactions. In practice, we want to just use some 1 body or 2 body Hamiltonian to model the system. We want to discard this other term. Then we can show within our method, the reconstruction error will be upper bounded by the ratio of the magnitudes of C prime over C. What this means is that our method is good as long as our initial ansatz is not too bad, meaning our ansatz has the property that C has a much larger magnitude than C prime. And these are basically what I want to talk about. So maybe the time is already over. This is the summary. I will not read it for you. Thanks for your attention.
Thank you so much, Liujun. So now we have time for a few questions. So, okay, I have a general question. So this approach that you guys developed, does it work like, okay, if you want to compare to extreme limits, like a Hamiltonian or a unitary, which drives you to a thermal state versus like a many-body localized Hamiltonian? In which regime does it work better? Or it just works in all regimes?
Many body localized Hamiltonians may be the non-generic case.
Oh, okay.
Those Hamiltonians are kind of having infinitely many methods to convert the quantities.
Right. Because you mentioned at some point the SYK model. Like, have you tried it, like on a SYK model? See if...
We didn't try.
What's that?
We didn't try. I was just saying our definition of local Hamiltonian includes the SYK model.
Right. It's the local in Hilbert space for number of operators.
Yeah, but we didn't benchmark it with the SYK model.
All right, if there's no other question, let's thank both speakers, Nat and Liujun. And thanks everyone for joining us today. So we'll have our next meeting in 2 weeks. Have a good day and see you next time.